Moving on to section B, line integral, interpretation and applications. So I will start by giving you the formal definition of a line integral. Please remember, same thing as it happened in one-dimensional integrals last semester, the definition was in terms of Riemann sums. Then for multiple integration, we also had these definitions which were also limits. And I'm going to do exactly the same for line integrals. This doesn't mean that you need to calculate any limits when you are calculating the integral. It's just a way to give you the formal definition, right? So it's not relevant to problems and to exams, but it's relevant for your understanding of what an integral really is, okay? So what is a line integral? Suppose that I want to calculate the integral along a curve of some function of the parameter u with respect to the line or to the curve. And we usually use the symbol dl to represent a differential of length of the curve. Okay, so this is how you write the integral of a function along a curve. So what do we do then? What's the definition? So here we have the curve. It's the black curve here, which is a function r of u, where u is the parameter. Okay? So what we do is we, instead of considering the infinite possible values of u, we discretize the values of u. In other words, we break down our curve into segments. Okay? So we fix certain values of u, which would be the red circles here. So we fix certain values of u. And now this means that we are dividing our line into segments, which are the red segments that I'm showing here. Straight line segments. Okay? This is a curve in 3 dimensions. Now for each of these segments has a certain length, which we call delta L1, delta L2, delta L3, and so on. And also in each of these segments, for example, consider our first segment here, we find a point. Normally we took the middle point, although according to a formal definition you can take any point inside the circle, inside the segment, but in this case we are taking the middle point. Okay, so the first segment, which goes from this value of u to this value of u, we choose the middle point, which would correspond to some intermediate value of u, which I have called u1. Okay, so u1 corresponds to some intermediate value here. So now we have this u1, u2, u3, u4, and un, because we have divided the curve into n segments. Okay? So now what we do is that we say that this integral along the curve of fu dl is equal to the limit when the delta l's go to 0, means that we are cutting into smaller and smaller segments until at the end we have an infinite amount of infinitesimally small segments. But we do the limit of the sum of f evaluated at ui, where I goes from 1 to n. So for each segment we evaluate the function at the point ui, so u1, u2, u3, u4, and un, and then we multiply that by delta li, by the length of the segment. Okay? And when we do the limit of the segments going to 0, we find a value which actually doesn't depend on how we divided the segment, because we're always dividing it into infinitely many segments. So it doesn't depend if we choose the middle point or we choose some point to the right or to the left. In the end, when we do the limit, when delta L goes to 0, we always find the exact value of the integration. Okay? Maybe to be correct here, I just noticed that I have drawn the intermediate values of u2, u3 outside of the curve, but actually I should have drawn them in the curve itself. Okay? So this would be u2, this would be u3, and u4 would be on the curve itself, and un also on the curve itself. Okay? Okay, now I fixed it. Yeah. So we select values of u that are between the extremes of the segment. So we choose some center value of u, but we are still on the curve. So this is the definition for the line integral. Okay? In the next video, let's look at an interpretation of what this definition means.